move semantics, which really covers the topic of R-value references, move semantics itself, and perfect forwarding, and lambdas. So each of those is a fairly elaborate piece of the language and deserves a little bit of extra time. Of course, concurrency, we'll talk about that. Now, some of you probably attended the concurrency talk this morning, so that's already getting into the nitty-gritty. This is kind of going to back up and just look at the real basics of concurrency. So we'll look at some of the fundamental pieces and see how we might apply them. And if you understood this stuff this morning, then this won't be very interesting. But if you haven't seen concurrency before, this might set in a little bit better. Then the library. So all the stuff up to the end of concurrency is basically the language with some library support. Then we'll look at new aspects of the standard library. So what I've tried to do here is at least mention all the significant features. There's still a few things that just don't get mentioned, but for the most part, at least there's one line item somewhere on a slide, and I can talk about it a little bit. In terms of the approach, what I wanted to do is, rather than just show features, I wanted to try to establish a rationale for some of these features by seeing how C++ 98 is deficient in certain areas, and then show the solution in C++ 11. So I don't do that for everything, but that's kind of, whenever I can get away with that without making this overly long, I've tried to do that. Most of these slides were developed about a year ago and tested on these versions of GCC. At the time, concurrency wasn't actually part of the distribution of most compilers, so I used a just thread version, which is Anthony Williams's C++ 11 compliant concurrency library, to test all the concurrency stuff. The code excerpts are not completely self-contained programs, simply because a lot of this stuff is missing. So just pretend the appropriate includes and std : colons and usings were there, and then the code should work. But I didn't want to clutter the slides too much. All right, so a little bit of history. Of course, C++ was invented by Bjørn Stroustrup circa 1979. The first version was called C with classes. And then the name C++ was coined by somebody and adopted quickly. The first standardization was completed in 1998. So that's the old C++ that I'm going to be referring to. Officially C++ 98. There was also a bug fix, sort of a patch update, C++ 03. Collectively, I just call that old C++ because the language didn't really change. In 05, the Library Committee released their Technical Report 1, which defined the new library components that would eventually be standardized in C++ 0x, which ended up being C++ 11. Fortunately, a lot of those library components could be implemented in terms of the existing old C++ language, and they were. And vendors supplied them as a sub-namespace of standard called TR1, and gave the whole community many years to become acclimated to these facilities, things like shared putter and so forth, hash-based containers, etc. So the language continued to evolve towards standardization, finally ratified in August of 2011. And that's where we're at. The next steps will be a C++ 14, presumably, kind of a bug fix update, plus. So it's not going to be like 03, which just really fixed ambiguities in the standard. It's actually going to introduce a few new language features as well. And the library will continue to evolve through these TRs or TSs, or I don't know what they're going to be called. They seem to keep changing in their name, but there will be a specific report for, say, the file system library when that gets hashed out, perhaps networking, concepts, light. Each of those will be in the form of a library report or a technical specification that prepares people for what those features will look like when they're actually ratified into the language. So somebody, I think it was last year here, characterized what goes on in the standard committee, why these things take so long, and basically they said, you know, the ISO committee, when things have to be agreed on, it's an international treaty. And there's a lot of politics involved in going back and forth. Representatives go back to their countries, get things ratified, come back. So the library folks like Boost, of course, don't like to sit back and wait for decades for things to happen, and all sorts of new facilities become invented, and then they make it into the language, kind of the fast track. relatively fast track. So goals for C++ 11, and these are pretty much taken out of Bjarne's C++ fact document on the web, which is really sort of the central repository of philosophy for C++ 11. Make C++ easier to teach, learn, and use. So when this was coined, one of the features that was going to make it easier to learn and use, presumably, was called concepts, and at the 11th hour that specific feature got scuttled from C++ 11, but hopefully it'll be improved upon. There was a reason it was scuttled, and it'll be improved upon, and it'll be introduced into a later version of the standard. Maintain backwards compatibility. Now this is a biggie, of course, in modern languages. You can't break the existing code base, but it's a real challenge to introduce new functionality in a way that's somewhat legible and intuitive, and still not, break code that existed before that. So every new iteration of the standard has to work with that challenge. And one thing that the C++ committee did for C++ 11 that I think is great is they introduced this concept of contextual keywords, which are keywords that only have their meaning in a certain context. They're not a universal keyword, so you can still have a variable called, using one of these words, but you can also use it as a modifier for declaration, and then it means something else. So that was a big step forward to keep things legible, keep them intuitive. Improve performance. Of course, that's always the holy grail, keep performance as good as you could keep it. Probably the single feature that has the most to contribute to this is R-value references and move semantics. So we'll see how that works. Strengthen library building facilities. There's been several kind of holes in old C++ where it's possible to write code where you're attempting to apply certain object-oriented rules that the object-oriented community understands, but there's no enforcement of those rules by the compiler. And this led to bugs and confusion, and you end up having to write a lot of comments, and the compiler doesn't honor those, of course. So in 11, some new keywords, some new facilities were introduced to plug some of these holes, and this is where those contextual keywords come in. And it really helps the robustness. The last one, interface more smoothly with modern hardware. I just see that as code for support concurrency. Modern hardware is moving toward multi-core processors, and without some sort of concurrency support inherent in the language, it's all going to be a morass of incompatible interfaces. So even though the industry kind of coalesces around a certain interface, it's nice if it were codified into the standard, which it has been in 11. Thank you. So Bjarne says, the pieces just fit together better than they used to, and I find a higher level style of programming more natural than before and as efficient as ever. I think there's a little understatement there. I believe it's more efficient, and Bjarne is just being modest about the efforts. All right. Part 1, we're going to look at some new keywords, auto-decal type, and the syntax for trailing return type for functions and lambdas. The null putter keyword, the new range-based for, affixed to an annoying little problem in old C++. Static assert, which brings compile time asserts into the language. Extern template, which solved a problem that had caused a lot of grief in terms of what's the most efficient way to compile and reuse templates. The no except keyword, which solves a problem that was also causing a lot of grief due to some issues with the old C++ exception specifications. Variadic templates. I included this in the simpler features, but they kind of straddle the simpler and the more elaborate. But this is where they ended up. Okay, plus a few other minor things. Let's start by looking at a piece of old C++ code. Now this is not a function you'd probably ever actually write, because rather than writing a function to do this, you just use an algorithm directly. But I wanted to do something fairly simple so I could introduce features into it. So this isn't an example of why you'd write a function or a function template, but it serves the purpose of illustrating these features. So generally when the text is in white, that's what I'm trying to highlight for that particular slide. So here's a function called find null. Assuming you have a container with pointers in it, find the first null that exists in that container and return an iterator to it. And if there's no null, then just return end, which is the convention for not found. I hope everybody sees this is not an algorithm, right? Because it doesn't take iterators as input, it takes a container. So it's just a function template that is algorithm-like in some of its aspects, but it's not an actual algorithm. Okay, so we're going to take a reference to a container, and we're going to look through it for an iterator, look through it for a null pointer. So the old way to do it is first we have to declare what it returns. Well, it's going to return a const iterator. It's a const container, so we should be returning a const iterator. We need to declare our variable. Now, what's this type name here? Well, it just turns out that in old C++, whenever you declare something whose type is dependent on a template parameter, it opens up this whole can of worms because of something known as two-phase translation. Two-phase translation is that the compiler has to process this source code once, just sort of to do a syntax parse, and then later it's going to process it again when it's actually specializing the template for some specific container type. During that first pass, if you have an expression like cont, which is the template parameter, colon something, the compiler doesn't really know what the nature of that something is inside the context of that class because the class hasn't been specified yet. Right? We're just doing a syntax check. So the language rules state that if this thing represents a type, you have to say type name. Otherwise, it assumes it's something else, like a static data member. If it assumed that here, that it would yield errors. It takes a lot of explanation for that, doesn't it? That's kind of the point of this. It'd be nice if no one had to worry about stuff like that, right? Okay. But for old C++, we have to say it. So we declare it with the same type. That's our temporary iterator variable. We're going to run through looking for a null. If we find it, we return it. Otherwise, we're going to just naturally return the end iterator. By the way, how do we test for null? Well, 0 always works. Some people in old C++ prefer to say capital NULL, and that usually works, and these days probably always works, but there was a time when it didn't always work. And that was a can of worms as well. In any case, 0 isn't very intuitive in terms of being self-documenting that we're talking about a null pointer. But still, in old C++, that was pretty much the most approved way to do it. Okay, so now let's take a look at a piece of code that actually uses that function, and we're still in old C++ here. So first, we're going to create a vector of some kind of pointer type, int pointer, and we're going to populate it. Well, there's a couple of different ways to populate a vector with specific values in old C++, and neither of them are particularly elegant. The first is to create a native array, right, which will use brace initialization, and then initialize the container from that array. Or you could just individually push the elements back one by one. That's the way I chose to do it. So the main function here will call find null and capture the result. And again, we have to declare what type that variable is in old C++. We check to see if it was end. If it's end, no null pointers. Otherwise, let's say we do find at least one null pointer. We'd like to tell the user what's the index position of that null pointer inside of that container. Well, we have the information because we have an iterator to the null pointer that was found, and we know what the index is of the beginning, which is 0, so we can subtract those two. But in order to subtract, what's the data type? Well, to be kosher here, we're supposed to use something called the container : difference type in order to represent the difference of two iterators to a particular container. If you did a size t, okay, it would probably work. In fact, there's probably no system on which it would fail. But technically, you're supposed to do that. From my understanding, the reason the standard came up with these different types, and I'm sure John can correct me if I'm wrong, but in a system that uses really large data, where 32 bits isn't enough to represent a size or something, 32 bits isn't going to be enough. So a difference type could be a 64-bit type or something. Same for any of those other type defs. So to be technically fully portable for 30, 40 years into the future as data sets grow astronomically, that's the right way to do it. Again, it takes a lot of explanation, doesn't it? All right. So now let's move to C++11. So the first thing I'm going to do is simplify the initialization. And no, I haven't officially covered uniform or brace initialization, but you can probably look at that and figure it out, right? It's not rocket science. It's a nice simple syntax that works with standard containers and lets you specify initial values using braces. Next thing is the auto keyword. So although the standard committee tried as much as possible not to break old code, there are exceptions. And if somebody insists on using the auto keyword in the C, C++ 98 style of auto, it will no longer work in C++ 11. How many of you actually know what auto does in C and C++ 98? Right. Don't worry. You don't need to know. Okay? Because you're not going to use it anymore. It was actually deprecated for C++ 98, so you weren't supposed to use it technically. But you could still. Well, now you can't. So the new meaning of auto is compiler deduces the type, so you don't have to actually write it all out. It simply looks at the expression used to initialize something and figures out what the type is supposed to be. There's a little more to it than that, but that suffices for this use here. So CIT is whatever find null returns. And the compiler always knows what the return type of find null is because that's the rule in C++. You're not allowed to invoke a function unless it's been declared. So the compiler must know what its return type is, and it just uses it. So nothing really new here. When we find that null pointer and we want to show the index position now, again, the type that's used to hold the difference of two iterators, let the compiler figure it out. We don't have to remember difference type and type out container : or any of that. Just auto, it'll figure it out. So there's a couple nice little improvements.
One question.
Yeah, sure.
On the brace initialization, what are the rules or limits around that?
Okay, the question is, what are the rules? I remembered. What are the rules around brace initialization? There's a bunch of them, and we're actually going to cover brace initialization in gory detail a little later. So in terms of to get some idea of what you're... Yeah, okay. I mean, there's a lot of rules. Are there a specific rule that you were thinking about? Okay.
No, essentially what kind of containers and classes can you apply to?
Oh, pretty much anything, because if it's a standard library component, it's been adapted to support this. And if you write your own classes, you can write them in a way that supports brace initialization. It's a little bit of a trick. There's an overloaded constructor that takes something called an initializer list. And then that's a feature that's kind of half in the library and half in the compiler. Okay?
Did you say we're going to be going into more detail with auto, the auto keyword?
Not much, a little.
So can I ask a question
Sure.
about it?
Uh-huh.
There are some APIs that expose two different functions, one being something that returns a reference to something, like say a vector container, which returns a reference to like a value at a certain index, and then another which returns a copy of that. Can the auto keyword deduce that somehow and decide whether to pull the reference out versus a copy?
Well, when I run through the cases, the question is, can auto differentiate between maybe overloads of something that appears over here? Would that be a way of shortening the question? I think in any case I could just think of when I run them through my head mentally, yes. Does that make sense, John?
Well, the compiler, when you declare a function, it can't be different just in its return type.
Sure.
So any function you define is going to have a specific thing that it returns, even if it's overloaded.
Right.
So in any given case, there's a specific thing that the auto will need.
Right.
You
So
can have a const member function versus a non-const, and they could still have the same function definition, right?
the question is if there's both a constant and non-const, yes, but then whatever the expression is over here that this thing is being initialized from, the object will be const or non-const, and that will resolve to which of those overloads get used. So basically it should always be able to figure it out, and if it can't, then you'll hear about it.
Okay, thank you.
Question?
Two autos. If, for example, someone will change find null to some other type, and the next auto defines as a difference between CIT minus leading. So if CIT is not an iterator, will there be warning or error?
Sure, because this actually is just, the question is if you then try to set CIT to something with a different type, right? Is that the question? Okay. Just as if you declared it as a double and then you try to set it to a pointer, you get an error. So all this, well, the second auto is for a different object.
We have a difference there. So, for example, if I modify the find move to return a double, then it will work for the first auto. The CIT will be double. Will be warning or error.
I still can't think of a situation where if the compiler looks at the expression over here, it can't figure out the type and then just understand that's what auto means, is whatever the type of this expression's result is.
But there can be an easy error. For example, if I do change it, I'm assuming the false is going to be a difference type, right? But if I change my CIT to be something valid, but not feasible for the second auto, I can be in trouble.
Like if it returned an integer index into the vector.
Yes. Because begin is
If this expression compiles, I mean, if the compiler can understand this expression and it has an unambiguous type, that's all that matters.
yes, but it might not be type that I expected.
Okay, then you got a bug. But that's not the compiler's fault.
Will there be no warning or anything?
Probably not.
The compiler can't know what you expect.
Yeah. Okay. One way I've heard auto described is if you're familiar with function template argument type deduction, you know what it is, how the compiler determines what the actual type is of a t parameter to a template in a function template. The same rules apply to auto, and so it's a deduced environment. It looks at the actual expression and deduces what the type is. Okay, we're probably not getting into some of the more elaborate auto, but you can say things like auto ref and const auto ref, and it can deal with that as well. You know, it just makes the appropriate adjustments, which is exactly how function template type deduction works as well. Okay.
Can I ask one more question?
Sure.
From a software engineering perspective, redundancy is sometimes good. If it's very difficult to understand what the return type is of the function and you repeat it there, when it's simple and short, does that give you an advantage as compared to, let's say the return type is some god-awful template expression that's 3 pages long?
I think the question is there going to be some potential confusion maybe by the use of auto? I think it becomes just a idiom, and it's not there yet. So if you're used to it not using auto, it takes a while to sort of transition. But I've seen lots of writings on auto already where, like if you look at Herb Sutter, he just uses it everywhere. He just gets used to it because it's so much easier to just put auto out there than it is to think about the type.
Right, but it's not easier to read. That's the thing I'm concerned about, that it can be overused. It's just, again, it's an opinion, but,
Yep.
but auto is good when the thing that you're trying to create is extremely complex and you know it's an iterate or
Right.
two away.
So I'm going to have to put that into the realm of it's a religious issue.
Gotcha.
Okay. New feature here. Sometimes a return type simply cannot be expressed in old C++. If you have a function template that takes two objects of type t and you multiplies them, what's the type of the result? Right? These could be user-defined types like matrices of some arbitrary dimensions, and the result might actually be a type different from either of the two operands. That's perfectly feasible in a matrix library. That's tough. So here's another use of auto. Don't let the fact that it's auto fool you. The standard committee likes to overload reserved words. So this isn't, no, but that's a good thing in many cases. And in this case, auto really means defer. Okay, so rather than specifying the return type right here, auto just means hold on, I'll tell you in a minute. And then that's in combination with this other little piece of syntax, the arrow, which is called trailing return type. So, you know, arrow int would mean the function returns int. Well, if that was the case, you could have just written int. So there's really several features working in concert here. And the third one is decal type, which will take any expression, either a type or an expression, and determine its type. So in this case, the type is this expression represents whatever the type of t times u is. So the magic here is that at this point T and U are in scope because they've been declared, so now we can use them to determine their type, and that's why we're deferring the return type from back here to over here, because now we can express it. Solves the problem. And it's free. It's one of these compile time facilities. It doesn't cost anything except compile time cycles. Okay. So let's start and morph the find null function template into C++11. So first we'll use the trailing return type. And I can really choose anything here that gives me an iterator. I just happen to pick c.begin. I could have used c.begin, c.end. I could have written it all out the old way, whatever. Again, we don't have to worry about this having the overhead of calling the function because this is just determining type. Think of it as analogous to size of. It's actually analogous in a lot of ways, where it's all a compile time operation. There's no runtime cost to that. So whatever cbegin returns, that's what find null returns. And so far we haven't changed anything else. So that's just applying the trailing return type. Another new feature, non-member begin and end. So 11 supplies begin and end that are functional. When applied to a container, they work exactly as if you said container.begin, container.end. It's just the syntax is flipped around. So here's our container v. We can say begin v. That is exactly the same as saying v.begin. And end v is exactly the same as v.end. So just for v, there's no real advantage. But the advantage is that you can also apply these to things like native arrays. So in this example here, we have names, which is an array of 3 C strings, right? And if I want to apply some sort of operation to it, I want to use the findIf algorithm, for example. I can now say begin names and end names, and it's a natural adaptation. If you recall what you had to do in C++98 to do this sort of thing, it was a pain. You actually had to compute the length of the array. There's a couple of different tricks you could use. And then if you change this by adding extra elements, make sure you've computed in a way that adjusts to the change, right? Well, you don't have to worry about that anymore if you use the non-member begin and end. So I believe the convention is to just start using this everywhere. It's like once you see this, you don't ever need the old style member function begin end ever again for anything. You might still choose to use it because it's an old habit, but you don't need to. If you switch this to everything, it'll work. And again, no cost.
Yeah, I have a question. What happens when you call begin or end on an empty container?
Okay, question is what happens if you use this on an empty container? Exactly the same as what would happen if you used member begin and end, because they're equivalent. Okay, so that's a non-issue really.
I mean, like on a static, like the const character names.
Yeah, well, the findIf algorithm works correctly with a 0 length range. It would work. It would return that iterator. It wouldn't find it because you've given it a 0 length range to search. So it really is equivalent. Okay?
Does the begin and end forward to the member begin and end? If it's
Yes, exactly. That's all it does.
Okay.
And the real benefit is if you can write a template using non-member begin and end, and that template will now work with containers and native arrays. So it really generalizes it better.
Kind of like swap.
Yeah, exactly.
Okay.
Okay? So, null pointers, all right? The whole idea of null pointers, in C it was really simple. A null pointer could be represented in a way that was consistent. Well, even in C you'd run into some, well, no, there's no overloading in C. So yeah, in C things were simple. When C++ came along, what was people had to come up with some sort of a way to represent a pointer that's null, and this NULL symbolic constant was created, and it turned out that it just had some funky incompatibilities with library components in various early versions of C++. So sometimes it wouldn't work as expected. And when you just use 0, which would always work, then it's not very self-documenting. So just to illustrate the problem, if you have overloads of f, one that takes a long and one that takes a pointer to character, If you call it and explicitly state you're passing along, that's unambiguous and fine. However, if you just say f of 0, this is going to be an ambiguity, right? Nature abhors a vacuum, C++ abhors ambiguity. So this is a fatal error. It doesn't try to read your mind, thinking, well, 0 is probably, they probably meant a char star. So you end up having to do either a static cast or just the old functional cast or something to disambiguate. All right, so potential for confusion there. In C++11, the new null putter keyword was invented to represent a null pointer only. It can never convert to an integer or an integral type. So now if we have these two overloads, if we call f with the explicit long, it still works fine. If we call it with null putter, it unambiguously matches the char star overload. If we call it with 0, it's still ambiguous because, after all, code has to be backwards compatible, right? But we wouldn't do that. We would use null putter if we want to take advantage of the new language. So now we can just finish up with the last version of find null. We're using the functional begin and end, new style begin and end, use null putter instead of 0, and that's it. So that's really about as far as we can go with this, but it was just a little bit of a showcase for some of these facilities. So good place to stop. Any questions about any of these features so far? Yes?
You said the begin and end will work with native arrays.
Right.
What about the iterator?
Okay, so the question is, will non-member begin and end work with iterators? Why would you apply them to an iterator?
Well, if this is a template and it's applied to a native array type, for instance. I mean, you're incrementing.
Since it makes no sense to say iterator dot begin, it wouldn't make any sense to say begin open paren iterator. Is that what you meant?
Talking about what if
The
C
plus IT, yeah.
makes C a native array?
Okay, so will find null work on a native array? Well, no, because this is declared as a reference to a const type. So,
It could be an array.
maybe it could be right. I never thought of that.
Well, I guess the begin C then would return an integer.
Well, the begin C would work if this was an array, but I'm just not sure it would ever, you know, it would ever specialize with a native array because I haven't really thought of.
What is
I think what he's asking is, what's the iterator for an array?
Oh,
And it's
Just
a pointer.
pointer, yes.
right. An iterator for an array is a
I
pointer.
think that's what he.
Okay.
What does begin returning?
Right. Right. So if you have an array of ints, right, and you say begin of A, that's a pointer to int. It's actually the same as for a non-debugging vector, typically.
So that the plus it is just incrementing the pointer into that array.
Sure. Plus, yeah, this is incrementing whatever it is, if it's an iterator or a pointer. Remember, iterators are pointers. Pointers are iterators when they are. Okay. All right, so let's look at a new feature. Iterating over an array or container. In old C++, here is an old native array being initialized. And this is what you had to do to determine how many elements are in the array. You had to do something like divide the size of the array over the size of its first element, right? There's variations of that. You can play games and write a template to do this for you, but basically it ends up doing the same thing. Okay, then we use an old-fashioned for loop to iterate. Everybody's seen stuff like this. In this case, we're using the new initialization just because it's easier to express on this slide. And then we use for loops to, let's say, modify each element of a vector, display each element of a vector. So this is kind of idiomatic in C and C++ to iterate over a container or an array using a for loop. Of course, it's also idiomatic in C++ to use STL algorithms for that, but that notwithstanding, we're just going to look at a better way of doing a manual loop. So C++11 provides this range-based for loop. The syntax is simpler. You don't have to supply the limits. You don't have to supply the initialization, the increment, the test, etc. You just say for, and then you can declare the actual type of the loop variable. For an array of ints, that would be int. So you could say for int I, and that's legal. But again, in the spirit of using auto in any place it can possibly be used, auto works just as well. So I will take the value of each element of AI. And this is the default mode where it's by value. So it's going to make a copy of each element in AI, and I will be a copy of that value. Clearly for ints, making a copy is cheap. If this was some more complex container type, then making copies might not be desirable. So in that case, you might choose to use a reference, and a reference to non-const could be used to modify. We could make this reference to const, and then we wouldn't be able to modify, but we'd be able to read, and it wouldn't be making copies. So you have all those usual variations. Then this will just dump each value, and just to show, you can also combine the range-based for with things like initializer lists. So this is actually a component, a construct called an initializer list. It's not really initializing anything except itself, but it's a list of ints, and we can iterate across it. Now this one's pretty simple. You used to have to do that. Now you don't. Any questions? Okay. I find myself still writing that once in a while. It's just like old habits die hard. So C introduced the assert macro. Assert is a really nice runtime debugging tool that simply tests some condition, and if that condition is true, it's essentially a no-op, other than the CPU cycles that it takes to test the condition. If the condition is false, then the assertion is false, and presumably that means something's wrong in a big way, and it'll stop the program with a nice diagnostic. So it's been around forever. It's actually one of those few things that's pretty much just as useful out of the C library than to rewrite it in C++ somehow. So it's actually a macro. In fact, it's more than it's a macro with conditional compilation associated with it. So you can turn all the asserts off and make them generate zero code in a release mode. But that's great for runtime, but there was nothing equivalent until C++11 that would work at compile time. It would also be nice to be able to test some condition and get an error message from the compiler that would essentially represent a fatal error if the condition was not met. So if a compile time assertion was not satisfied, we wanted to be able to deal with that. And that's exactly what we have. It's called static assert. This condition must be comprised exclusively of constant expression elements. So whatever's in there, it has to be evaluatable at compile time. Now in C++11 there's actually quite a bit that can be evaluated at compile time. Like even functions can have compile time evaluation capability, which wasn't true in old C++. So there's quite a bit that you can do with this. All right, so let me show you some examples. So here's a nice simple one. If you have some sort of an app where you don't want it even to be compiled on systems that don't have at least 32-bit integers, this line will basically nip that in the bud, right? We're asserting that the size of an int is at least 4. If that assertion is false, then we'll get a fatal error, this message will appear, and it won't go on to link. The next example, I actually stole this approach from a course I teach by Steve Dewhurst, where this was done pre-C++11. And what Steve wanted to be able to do was write a template that performs a cast that does just some rudimentary safety checking. And all it really is going to do is to make sure that whatever you're casting to will, in terms of bits, hold whatever it is you're casting from. Because the native casting rules of C and C++ let you cast basically from anything to anything, and they don't do any sanity checking. So you could cast from a double to a bool. That's perfectly fine. You don't even have to cast, which is really sick. Anyway, what we want to do is let the user say safe cast, to int from that. And if it's impossible, this could possibly fit into an int, we just want to compile time error. We don't want to waste runtime cycles. In the original version of this, it threw an exception, because that's the only thing we could do before we had static assert. So the function template would determine whether the thing was going to fit and just throw an exception if it didn't. Okay, but in C++11, we can take advantage of this wonderful static assert. So we assert that the size of the result is going to be at least the size of the expression we're reading from. And if that's false, we just stop right here with a fatal error. Otherwise, we go ahead and we perform the static cast. All right, so safe cast from a long to an int will succeed if long and int are actually the same size. If you're on a 16-bit machine, this would fail, a typical 16-bit system. On the other hand, this should never succeed. All right. New feature. So a little bit about templates and code bloat. There's actually two different ways for templates to be processed in C++. Historically, the very first implementation of templates actually used separately compiled templates. When you compiled a template, it would actually store it like an object file. And that was the C-front implementation early on. The problem with that was, because of this two-phase translation I mentioned earlier, that templates have to be processed once to check their syntax, then a second time when they're specialized. That approach became really expensive and flaky. I remember teaching a course once when people used C-front for templates, and I saw these problems. Templates were just not working right. And it had nothing to do with the course material. It was just simple templates wouldn't work. So the industry has settled on the other approach, the inclusion model, where you include a header file with the full implementation of templates. And it seems like that's an awful lot of code. Wouldn't it be nice if that could be sort of separately compiled? But at least it works with the inclusion model. Yes, it's a whole bunch of code that's included in every translation unit, but it works. But there's a price for that. Because templates were fully defined in header files, each translation unit required the compiler to perform a whole lot of compilation on all that template code, even if it wasn't really needed. So you end up with a lot of the member functions of the template compiled duplicately, right? If you have 100 modules and you're compiling each one separately, each one of those is going to fully compile a lot of the member functions of that template. And then the linker will, basically see duplications and throw all but one away at link time. And that's not real efficient. So at link time, all but one instance of each of those member functions is thrown away. Yes, there's precompiled headers and there's optimization tricks. Compilers have tried to address this, and it's been, I guess, somewhat successful, but it's still a fundamental problem. So the C++ 98 standard at least wanted the option to be available for people to use the separately compiled template model, and that's where the export keyword was designed to do. Now, the problem with export is that the committee basically said, we assume that compiler implementers will figure out how to do this. And in fact, they did, but it took the one implementer that actually succeeded about 2 or 3 man-years to do it. And when they finally got it to work, it turned out that there was no substantial improvement in overall productivity from employing that feature. It wasn't worth it because of two-phase translation. So, well, to make a long story short, the feature has been discarded for C++11. It's not even deprecated because it was really just not a useful feature for compilers to have to support. Okay. Fortunately, another solution was come up with that actually addresses this in a very, very elegant manner. And it's the extern template declaration. In a header file, you include the header files for your library components that you need. And then in every individual translation unit, except for one, or maybe even in all of them, you write extern template class vector widget. So what this tells the compiler is that the actual implementation of vector of widget, the specialization for that template, will be generated elsewhere in some other translation unit. If you've got 1,000 translation units, 1,000 modules in your program, and 999 of them say this, then the compiler cannot bother generating the member functions for vector of widget. It simply just generates the references and lets the linker deal with it at link time. Then in one translation unit, you supply this after the includes, instead of this, or in conjunction. I think you can actually do both. But the key is that this only appears in one CPP file. Template vector widget. And this is called explicit instantiation. So this forces all the member functions to be generated. If some of them aren't used, yes, that could be wasteful. But the overall benefit here is dramatic, because in 999 modules, it didn't have to do all that compilation. Also, presumably, on a system that big, you may not have too many member functions you never use. So even if you have a few extra member functions in there, it's probably not that big a deal. Okay, but that really solves the problem really nicely that export was originally kind of designed to deal with. Is that a fair simplification of this whole story? Because I know there's more to it than that, but I'm really just trying to cut to the chase on all of these. John didn't say no, so I'll take that as a good sign. Yes?
In a large system, what's a typical way of organizing that? Do you have a file that's like vector widget.cpp, and that's where you put the...
The question is, how is this organized? Well, remember, the actual template code is still in the library header file. I mean, in vector, you still have that code. So you really would just do what you normally would do, except for the addition of this one line in most of the modules, simply to keep the compiler from generating, from actually instantiating those member functions.
So do you have one specialized translation unit for that template vector widget?
Well, that's essentially what this ends up being. This is the one translation unit that gives the compiler the go-ahead to actually generate all those member functions.
And if you forget to actually use that template vector widget, you get a link error?
You'll get a link error, yeah. There will be missing a bunch of unresolved references. And it should be really obvious, because they'll all be from vector of widget or whatever.
I wanted to make a suggestion, the way you might explain this.
Okay.
Suppose I'm a compiler vendor, and I know that vectors events are really always used. So in my compiler vendor approach, what I'm going to do is I'm going to create my template, vector template thing. I'm going to do all of that, but in the CPP file for vector, vector.h, vector.cpp, you can put that instantiation, so when people link against vector, quote unquote, in the standard library, that's where the data will exist. And it's okay for people to see the definition of vector, and then that extern says, no, I'm not gonna have the compiler instantiated in any translation unit that includes vector. And then when you use that final one, it overrides the extern and says, oh yes, go ahead and do it. And it does so in its own section, and it does so with a weak symbol, so it's just as if it had done it in everybody's translation unit, but it does it in the one. That's how I believe it's supposed to be used.
Okay, that sounds good. I don't actually do enough large-scale development to be able to tell you what the best way to take advantage of this is, but yeah. I love this, and it's too bad for the EDG folks who spent 3 years implementing export. Question?
So I think John might have answered it. If I'm understanding correctly, if I had a header file that had that extern template syntax in it, and then in my, say, CPP file that included that header file, I say template vector, that effectively overrides it.
Right, yes. Which is why I was saying you can have both of these, just like you can have an extern int x and then say int x right afterwards. Yeah. That's perfectly legitimate. So I presume the system is the same here. I'm a little bit reluctant to recommend putting this into a header file that then includes that. I mean, maybe that's perfectly fine, but I don't know. So you guys are free to.
Vector, if it's a standard library widget, of course, is a user-defined type.
Wait a minute, you can't go in and put anything straight into vector.
If you're a compiler vendor, I'm using vector.
A compiler vendor.
You create your own container. I create my container. And then I know I use my container on widget, let's say. And I say that happens all over creation because that's what I do for a living. Well then, my container, when I include my container, I'm going to specialize it on widget because that's really important. We are tying two things together. It's much nicer when it's a fundamental type and a container type because then you're not tying anything together. So for vector of int, there's no problem. You see what I'm saying? Or my container of int, there's no problem. As soon as it's my container of widget, now you have coupling issues that you have to worry about. So you have to decide, does vector depend on widget, or does widget depend on vector, or none of the above? If it's none of the above, then you have to separate them out. That's a levelization issue.
Okay.
What does that buy? I mean, if the vector includes that, if the library starts having its own CPP files, then you are essentially going to have to link to an external library, which is the whole point of the template library.
No, I'm pretending that I'm a compiler vendor. No, I'm saying I'm shipping Microsoft's vector. So the way it looks is there's vector.h, if you will, or vector, and then in the corresponding CPP file, there's one implementation. But everybody who includes vector, there's no vector of int being created in their stuff. There's just one. So I'm saying if I'm a compiler vendor. Now, if I'm my own, I'm writing my own code, then I have my own container and I happen to use it with ints all the time, I can do the same thing. For your own container with a fundamental type, there's no coupling issue. That's how you do it. Typically, it would be something like an int and a string would be the ones that you do it for. And then that's it. It's like a hash table of entry, hash table of string.
All right, let's continue this offline, maybe on the break, for those who want to. Okay, one more thought.
The way I would use that is I would have my widget library, right? And my widget library, I've got a vector of widgets is one of the fundamental types. I'm going to put that right in the header so that all of the from creation libraries that deal with widgets don't have to expand the template. And then I'm going to, in the widget library, expand the template and get the linkage, because everybody that uses the header for widget is going to have to link the widget library anyway. So it seems to me that would be the primary use of
It's reasonable.
Try it.
Just clearly below widget, right? Vector
Yeah.
is a standard thing, and widget is my own proprietary thing.
Right.
So it's fine.
Okay. All sorts of possibilities open up. That's the nice thing about this feature. So let's move on to a different one. So just as there was a core problem with this export keyword in C++ 98, there's another kind of core problem in the old language, which was exception specifications. Now, how many here know Java? Just to get a rough idea. Okay. Not all that many. Exceptions, are a syntax that's very similar between C++ and Java, but there's a fundamental difference between the two languages in terms of how exceptions are dealt with. In Java, when you write a function and it declares that it's going to possibly throw some exception, a caller of that function has to acknowledge that. They can't just blow it off. They can't say, oh, I'm not going to worry about it. They have to either say, I will handle this exception if it gets thrown, or they have to say, I'm going to propagate it to my caller. One of the two. And if they don't do one of those two, it just doesn't compile. And that's a rule that C++ has never had. And that alone makes exceptions problematic. On top of that, in C++, the way that you do specify what sort of exceptions you're going to throw has some real downsides, because if you didn't have templates involved, then yeah, maybe you can say that a particular function throws a particular type of exception. The exception specification syntax allows you to name an exception type in these parentheses. And so if I had some non-template class called my container, and I could say swap throws a bad widget exception or something, and that's fine. But when you start writing stuff in terms of templates, you're generalizing. There's no possible way you can declare what type of exception is going to be thrown from a function where you're dealing with objects of some unknown type with operations and you don't know what their exception behavior is going to be. So immediately the whole idea of declaring a list of exceptions that you throw becomes kind of useless in C++, and that happened when templates were introduced into the language. However, there was still one moderately useful form of exception specifications where if you know you're not going to throw any exception, you could use the empty exception specification. But that was just a special case of this general exception specification mechanism, which means there's still a lot of overhead that has to deal with all the possible permutations of multiple exceptions. And in the special case where there's just none being thrown, the code to enforce that was still rather heavyweight. So it turns out that in the C++ 98 standard, the only form of exception specification that's used anywhere is this empty one. And even then, it was less than ideal and optimal in the way that the code that deals with that was generated. So in C++ 11, taking all of that experience into account, what was realized is we just really need a way to say whether or not an exception gets thrown. And so the no except keyword was introduced. In the simplest form, no except specifies no exception will be thrown here. Now, of course, nothing prevents the implementation of swap to have a throw 25 statement in it. The compiler will accept that, I believe, but at runtime it will just terminate the program. So it doesn't really mean that there won't be an exception that takes place. It means that in a sane implementation of this particular functionality, it should never fail. There should be no way it could ever fail. So I actually prefer to think of no except as a no fail specification. Right? It says this cannot fail. It's going to be an operation it's only doing manipulation of built-in types in a way that can't possibly mess anything up.
Just a question. You just said, but if there's an underlying exception being thrown, say because of some memory tromping or something that happens, it'll just exit.
It'll terminate, yeah.
So then how's that a no fail?
Well,
Like it'll be like
it should be a no fail. The compiler won't enforce that, but logically I think of a no except as a way of saying this is such a simple operation it can't possibly fail. So all the pieces of work that it does are dealing with fundamental types in ways that can't possibly fail. So there won't be an out-of-memory condition, there won't be something else. Now if you have it like a divide by zero or something, technically that's not exactly an exception, that's just a processor fault, that's a different situation. Right? The exceptions are synchronous types of operations. They're based on a throw statement somewhere that gets executed.
From the old one, like no except from, say...
Because when you use the empty exception specification, the amount of code that was generated to actually do that in ways that supported all the ways that those specifications were originally intended to be used generates lots of complexity. Basically, when you have a throw, open, close, it's like a try-catch around the whole function, where at the bottom, if it catches anything, then it translates it into a specific type of an exception that means bad exception, or I don't even remember what it is exactly. But all that code had to be there, whereas no except is more streamlined.
What is the advice on when to use no except?
First, let me just say what its additional capabilities are, and you'll see that's not a simple question. Okay, so just saying no except is one way to use it. It can also be conditional, and I don't actually show an example of that, but you can make this no except conditional on the no except status of sub-operations of this function. If a function calls 2 or 3 other functions, then no except can actually say no except open paren, no except of the name of one function, comma, no except of the name of some other function, and it'll look at all of those various sub-operations, and if any of them is not no except, then this won't be no except either. Yes?
Yeah. So for swap, this is the perfect example, because what you can say is, oh, this is no except as long as whatever t is has no except move operation.
Yes, exactly.
Because if I can move constructed and move,
I was actually thinking of that as a good example, because move semantics, which we haven't talked about yet, in order to guarantee that an exception won't happen during a move operation, it must be guaranteed that every sub-object of the object you're moving doesn't throw an exception. So if you have, a move operation and it's implemented by performing a bunch of operations, the only way that move operation can say that it's no except is to specify the conditional no except on all of its sub-operations. The same for swap. When you're swapping an object composed of sub-objects, right? All of the sub-objects have to have no except swaps. And then the parent swap will be declared that way. So it'll be more complex than this. So this might be the lowest level one, where the implementation is an int or something. It can guarantee it can swap a couple of those without any exceptions.
So you're saying every function that I call, say, in that swap method would have to have the specifier no except?
Yeah.
Or it's a compile time error?
Or it wouldn't be no except, and all that would really happen is then moves would be less efficient, right? It wouldn't be able to use move operations. It would have to, step back to copy operations for those, when those things were in a vector or container.
But it should be a compile time error, right?
Only if the proper copy operation weren't implemented or something, because the whole move semantics is such that it uses move when it can, and if it can't, then it uses copy. But if neither move nor copy is available, that's when you get an error. But
I guess what I was trying to ask you is, whatever that function is, even if it's not swap, it's like my function. If all the sub functions that this function will call, do they have to have the specifier no except on them?
Only if I want to say that my function is no except and I declare it that way.
Yeah.
I would explicitly declare a no except that is dependent on the no exceptness of all the sub operations. And I just haven't shown that. And I've kicked myself the last 2 or 3 times I've done this, because it'd be easier to just show an example with all that. But I'm trying to keep it simple. Instead I end up spending 5 minutes talking about it. But, yeah.
So if you put no exception specification at all, presumably there's no overhead, right?
There's no overhead.
In other words, you don't have to have
Yeah, there's not going to be anything. Well, there's still going to be exception handling. If there's exception handling enabled in the system, there's all the usual exception handling overhead. It's just
there wouldn't be a penalty for that function. There would only be a general overhead that there is.
It's the other way around. No except eliminates most of the overhead. It doesn't eliminate all of it because it has to detect for the possibility of an exception, but it doesn't have to do anything but quit. So
Yeah.
almost all of the overhead is eliminated by using no except. Unfortunately, there's another issue, which is if you use no except in a situation where you have a narrow contract, which means there is the possibility of undefined behavior. Then, if you're outside of defined behavior and the no except is there, you're not able to detect that you're out of
It's
undefined
true.
behavior, and therefore, no except, it was decided, should be used only on wide or conditionally wide contracts.
Okay.
Which means something like the bracket operator for vector is not a candidate. Or pop, for example.
Well, I don't even know what wide contract means, so I'm going to have to agree with you there.
Okay.
All right.
It means that there's no possibility of undefined behavior.
Okay. Okay. So, any questions on any of the features we've covered? We're about to move into variadic templates. One of the fun things here. All right. So here's the problem. How do you write a function to provide the average of n values? There are solutions even in C. It involves telling the function how many items that you're averaging and then providing them all. This is the actual syntax, right? This is called a function with a variable number of parameters. For example, printf, scanf are defined this way. There's an initial const char star that represents the format, and then it basically interprets that string in order to determine what are the types of the things that follow. Very type unsafe, of course. So the only way this could be sane is if it only works for a bunch of integers. And the only way this one could be made sane is if it works on a bunch of doubles. So you provide a count followed by that many, exactly that many doubles, it'll work. But you have to write one of these for each type, right? You have to provide that first argument, and there's no type safety. So, yes, you can do it, but it's not particularly elegant. We can't use default arguments in C++ because a function that accepts default arguments has no way of knowing when it receives control how many were actually passed. That information's not passed to the function. So it always acts as if all the things were passed, and you can't do an average that way. We could use overloading and templates and some combination and maybe achieve an approximation, but they're all ugly solutions. So let's look at the way C++11 would do it. Well, to get an average, we have to start with the ability to get a sum. So we're going to look at how the variadic template mechanism can be used to compute the sum of an arbitrary number of values. As it turns out, they don't even have to be the same type. This slide doesn't underscore that, but they can be different types and this will work. So variadic templates are a recursive mechanism. Right? So anytime you have a recursive algorithm, you have the general case and the terminal case, right? So if you're going to compute Fibonacci recursively, you know the value of the first and the second Fibonacci, and then each one after that is based on a formula involving the ones before it. So that's how variadic templates work. The terminal case for the sum of n values is a single value. That's not even variadic, this is just an ordinary function template, right? Would everybody agree the sum of one value of value n is n? Okay, easy enough. Where the variadic comes in is down here. So variadic templates have a template parameter list and a function parameter list, which are parameters processed in lockstep. They're a matched set. So each of the types in the template parameter list represents, is associated with an actual function argument in the argument list. And these things are called parameter packs. Template parameter pack, function argument parameter pack. They're processed together. So imagine that, you know, the user said sum of 1, 2, 3, 4, 5, 6, 7. So that would be a match for this template, right, with the first type name t being an integer, and then this parameter pack representing the set of everything from 2 to 7. And in terms of, well, actually, these are all int because these are ints here. So then the arguments represent everything from 2 to 7. So it'll be int 2, int 3, int 4, int 5, int 6, etc. Okay, that's how those work. So how do we calculate the sum? Well, we have the first value, n, and the sum of all of these is simply the sum of n and the sum of the rest. So rest here represents these arguments, and it's recursive. And then the first one here becomes t and n, and everything except the first becomes the rest. So each time this recursively calls, it consumes, you know, one more of those leading arguments becomes t and ends up resolving to this. And eventually it reaches the end and unwinds and gives you the result. And it all happens at compile time. Any questions?
The syntax, dot, 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 and the dot, dot, dot is interesting to say the least. Rest is the name of the...
Well, of course, it's a combination of existing tokens, right? The word type name. Type name was already a reserved word. Dot, dot, dot was already a token to support, you know, C-style variadic functions. So it's just a new combination of those semantic elements.
But you see the dot, dot, dot is after the type name in one, and then it's after the args in the other, and then it's after the rest in the other. So it's interesting it's used.
Yeah. So this args corresponds kind of to with this arg, and then this rest corresponds to the list of these actual values. Right? So n plus the sum of all the rest of the values. So that's how you use these, and both of these will work, whether it's with ints or with doubles, or even if they're mixed up. I didn't show that, but it'll work if you have a mixture. In fact, there can be any number of different types as long as the plus operator is understood, right? For those particular combinations of types, it'll work.
So the compiler just generates this code as just like an unrolled recursion?
Yeah, when you end up looking at the generated codes, it's as if you wrote cout less than 1 plus 2 plus 3 plus 4 plus 5, except that becomes a constant expression. So it becomes as if you wrote cout less than whatever the sum is. And it reduces to just one constant value.
So isn't that going to be unsafe, though, if you mix the types? I mean, if your first type is an integer and your second type is a double, isn't it going to degrade to integer calculation?
No, because every time you end up here, the correct type will be corresponding with the appropriate value. Remember, it's a matched set. These are processed in lockstep. So the first arg is always going to be the first rest. The second arg, the second rest. They stay matched.
But what about stuff that can get cast to each other?
It'll apply whatever normal conversion rules it would, even if it wasn't a variadic template. So once you look at the generated addition operation, it would do whatever it would do if you wrote it out directly. Like, it'll apply the same rules of conversions.
So if I had int double int, let's just say I'm alternating int double int double.
Okay.
So it's going to go, the first return type is int, the second return type is double. The third return type is int, the fourth return type is double. Is that correct?
You're going to need to use decal type and trailing return to get it to work.
I don't think so, because I actually tried this with mixed up types and it worked. I wasn't sure myself. I wanted to run it and make sure, and it did work.
If you put the int first, it should work. But if you put the double first followed by an int, then when it peels off the int, it's going to return the int type, and you're going to lose the fractional part of the double.
Oh, okay.
It would be order specific. So the way to do it would be to have a decal type where you can return the type of n plus sum of rest.
Okay, thanks. if any place would find that, this is the place, this is the locale. Okay, so this is,
I
okay.
don't know how to fix it, but that's what I was worried about.
I ran this example by Andrei Alexandrescu,
Oh.
and he didn't catch that. Okay, so you're good, John. I figured if Andre would give it his stamp of approval. You know, the only reason I ran it by Andre was I was feeling like, am I overlooking something? Is there a simpler way to do this? Like, do you actually have to use variadic? I would have felt stupid showing this elaborate example using variadic templates when there's a much simpler way to do it. And in fact, well, I'll show you the next slide because Andre had an interesting thing to say about this. So all we did was sum, but really we're shooting for average here. But now average is really a simple extension. So here is the average variadic template. And notice I am using decal type here to return the average. It's whatever the decal type is of the sum of all of the arguments. And I know I can do the sum, so all I need is a way to know how many things were there, because I'm going to divide the sum by that number. Well, there's a special operator called size of ... Isn't that handy? And I can apply that to args, and it'll be 7 or whatever, 3 in this case, and it'll give me the right thing. So when I showed this to Andre, his reply was, oh wow, there is a use for size of ... He may have been kidding with me a little bit.
Does this have to be used with values that can be summed at compile time?
No, I don't think so. I think you can have variables there and it should work. Okay. There's nothing necessarily constant expression specific about this. I just happen to put some constants there so I don't have to have variables that I have to initialize. Yeah. All right. Isn't it kind of cool that with constants it all reduces to just a constant, like an immediate operand in a register, and that's it? All that. That's kind of why I like the example. Oh, moving from the elaborate to the less elaborate. There's some string-related features in 11. There's more types of text. So UTF-8, UTF-16, UTF-32 each has their own way of being specified here. And I don't work with those types of strings. So if you know what UTF-16 is, that's useful information. Raw literals. This is a feature you pretty much have to have if you're going to have regular expressions. And one of the things I don't cover in this overview is regular expressions, because that's complicated and takes a session on its own. But if you're going to use pattern matching using the syntax of Perl or something, there's all sorts of backslashes and things that show up in your patterns. And if you had to use the old style double backslash, to represent a backslash, those patterns would be essentially illegible. So for example, this is the old style way to represent this text. This line here, right? Backslash, colon, quote, backslash. So this text is in here. With raw string literals, you can actually just show it literally. And it's all delimited by a leading capital R quote, open. So these three characters are quote, open, and then close quote. So everything in between the parens is part of the literal string. So that will handle everything in the world except something that has to have a close quote in it. So if that's what you have, then you can go one step further and provide your own custom string to represent the delimiter. So this would be a literal string delimited with XYZ. So raw quote XYZ open, so it starts with and then it ends with this paren XYZ. So it actually ends with the exclamation point. This delimits the end. So, most of the time, all you need is this simple version. But if you have this sequence, this exact sequence in there, you have to move to this. And I believe you can have, like 14 characters here or something. If you can't come up with one that works, I'd like to see the application. So that's raw literals. All right, so enum class is a stronger typed enum. Enums historically were just like ints basically. So they didn't really have a unique type associated with them. You couldn't specify whether they're ints or longs or doubles. So the enum class mechanism was just added as a more robust, more strongly typed enum, that each one has its own distinct type, and you can specify what underlying integral type is used, which makes them a little more flexible. Const expression can be used to tell the compiler that a particular expression is compile time evaluatable. You can actually declare a function as a const expr. And if you apply that function to a constant expression, and you haven't made an error, by doing something that's not a constant type of operation, then it'll actually evaluate that whole function at compile time. Const expr functions will actually revert to ordinary non-constant expression functions if invoked with a runtime expression. So they're actually pretty flexible that way. All right, and long just makes it official. You can have 64-bit, at least 64-bit ints, long. Of course, they could be bigger. All right, so for a while, a proposal floated around that was known as the template type def. And so the idea was if you use some of the standard template, standard containers like map, for example, and you use a map of string to int, and you always want to use a particular comparator that orders in decreasing rather than ascending order, you'd like to be able to create a shorthand for a map that always sorts backwards, right? And then you can just say backwards map of int double or whatever. Now, there was no syntax for doing that, but now there is, and it's called the template alias. So the keyword that they finally decided to use, which is actually I think a great choice because it generalizes real nicely, is the using keyword. Again, it's just recycling that reserved word. So say using, and then your own name for your specialized container. Set greater than is a standard set of t, standard greater of t. And now you can just say set greater than of double. And it's as if you said, set of double, comma, greater of double. Now, just as in the same way that the type name keyword was originally designed so you can disambiguate whether something is a type or not a type for templates, and then it was retrofitted to be used in this context just instead of the word class, right? That's not the original use of type name. In the original version of C++, you had to say template class T. But once they had type name lying around, they said, oh, well, let's just allow people to say type name, because after all, T might not be a class, it might be int. It's kind of ugly to say it's a class when it's not a class, right? So that was a nice little cosmetic touch. Well, the using mechanism can also be used as an alternative to the old-fashioned type def mechanism. So here's the old-fashioned type def. Void func is a func taking no arguments, returning void. Right? Actually, void func is a pointer to a function taking no arguments and returning void. But somebody who isn't familiar with type def looking at this is going to get confused. I get confused looking at that. Well, instead, you can just say using void func equals, and then you can specify that declaration without the identifier, and that makes it really clear. Pointer to func, well, relatively really clear. Okay, maybe in this example, but imagine if this was a lot more complicated. Okay, this is going to be more readable, because it takes that identifier and puts it right here. It doesn't bury it in the middle of a complex declaration. That was the part that was confusing with the original type def mechanism. And finally, there's a line as and a line of, forcing and querying boundary alignment, if you want to line your data up on specific boundaries. Hello. I'm not clicking. Oh, I am. All right, so attributes. I still don't really understand exactly how attributes are used, but you can use these things like no return to help the compiler understand a particular function is designed not to return and perform certain optimizations that way. So I guess the general idea is to have attributes that are bracketed by these double square brackets that are extensible, and maybe platforms can add additional ones. There's only a couple that are standard, no return and like one other one, right? but it replaces pragmas in certain situations. All right, inline namespaces. This is another feature. It took me a while to remember what it's good for. What makes it, what finally made me remember is that it's a versioning feature. It basically says you can have different versions of a particular library, and one of them is the default, and then you can change that default by making it an inline namespace. And what technically it does is if you have a sub namespace, then if that sub namespace is inline, it acts as if it was declared hoisted up into the parent. And you can easily have 3 or 4 different sub namespaces and change which one is hoisted just by moving that inline keyword around. So as you have a new version of a library, you could install that as the default by putting inline on it, and leave the old ones around that people can still get to by name, but the new default will be the one that you specify as inline. Is that a good description?
So what's the syntax for that? You say
Um,
inline namespace?
Yeah, it's just the keyword inline right on the namespace definition. And typically it would be a sub namespace, right? So you're already in a namespace, like you're in standard, and then one of its sub namespaces would be inline and some others would not be. And
If it wasn't a sub namespace, you'd be putting in global. Right?
yeah, well, yeah, if that's even legal, I'm not sure.
So I think part of I think this is used by Howard in the Clang, well, in lib C++. And the cool thing about the way it works is that the caller doesn't know that this sub namespace is even in use. They just call it the regular way.
Right.
But the linker does. And so what happens is if you try to link objects with mismatching libraries, it'll fail to link. It's what you want to see. But the source code doesn't have to worry about it.
Okay. I see that we're a little behind pace here, so I'm going to try to do a lot in the next 5 minutes so that we're a little more caught up. So maybe for these 5 minutes, I'll ask for no questions so I can catch up. Generalized unions. Unions can have more things than they used to be able to have, like constructors. That's basically the idea there. Why do I keep losing? Oh, I know why. Okay, I should be back. Generalized pods, plain old data. That's what C-type structs basically are described as, and now there's a little more elaborate rules so that these kinds of things renamed as standard layout types can have constructors where they didn't used to be able to have constructors. They still can't have things like virtual functions and whatever, but there's a little more that they can still have. C++11 does supply a garbage collection specification for an ABI interface. It doesn't actually provide a garbage collector, but it provides the hooks where a garbage collector could be integrated if it's desired. Garbage collection sort of goes against the grain of C++ most of the time, but if you really like it and need it, at least now there's some official way to integrate that. User-defined literals are kind of a neat feature. You can come up with your own syntax for some arbitrary user-defined type. You just need a new trailing letter that isn't used already in the standard for some other built-in type. So you can specify a binary class, and then a letter B at the end of a constant would be legal syntax. And it's really kind of a trick because it turns out to be a string processing function that you write. And so that text gets turned into a string passed to your function, then you can parse it and turn it into whatever you want. But it's an interface that makes the source level look really clean. All right, let's move on right into class design features. So some new keywords for controlling some various aspects of classes in an inheritance relationship where that control wasn't really available before. Delegating constructors, which is Java-like, one constructor calling the other. Inheriting constructors, so you don't really have to reinvent the wheel if the constructors don't need new parameters, and some additional features. All right. So if you were in the concurrency talk this morning, one of the things that was mentioned was that in old C++, if you wanted a class that was not allowed for its objects to be copied, you basically had a choice of two evils in C++ 98. You could declare the copy operations private, which works for users but doesn't necessarily work for the implementer. Then you don't implement them. So that means that if you're an implementer, the code will compile but not link, so an attempt to copy one of these things wouldn't be diagnosed until link time, which is not ideal. Alternatively, you can inherit from a base class that has that has the internals to avoid copying. So basically the base class would do this inside of it, and if you inherit from it privately, that creates a nice uniform way to avoid copying both from clients and the class implementers themselves. The problem with this is inheritance is the gateway drug to multiple inheritance, right? So you really want to kind of avoid inheritance if you can. There's no other good reason to it. So the C++ 11 alternatives are the new equals default and equals delete syntax. And these apply to all of the normally generated functions. Right? In C++ 98, there's 4 functions that can be generated. In 11, there's actually 6 of them. So you can specify that the default constructor is going to be the default one. And there really was no way to say that before, right? You either had to just not mention it, or you had to declare it and then implement it. But there was no way to declare it and say just generate it the way you normally would. And now there is. It's going to generate the default implementation of that constructor. You can also say equals delete, which will exclude that particular function from the interface. And now the nice part is it can still be public and be deleted. So you don't have to mess with things being private, and you don't have to mess with inheritance. It just works. All right, so here we've eliminated the copy operations, and we've said we do want a default constructor, right? And because we have some other constructor